Okay, these are some problems from section 6.4. And exercises 1 through 10 use separation of variables to solve the initial value problem. Indicate the domain over which the solution is valid. So again, we have this differential equation, dy dx equals x over y, and y equals 2 when x equals 1. So those are my conditions, so I can solve this. I have a point on the curve, 1, 2. So again, we separate the variables, so this is going to be y dy equals x dx. Integrate both sides. We end up with y squared over 2 equals x squared over 2 plus c. We just have one c. We combine those. This becomes, then we put these on the left side, so just subtract that from both sides to get y squared over 2 minus x squared over 2 equals c. And I multiply both sides by 2. And I got a new c, so this is just 2c, which becomes a new constant. And that's basically a solution. Looks like it's going to be hyperbola. Then we want to find out what c is. So y is 2 when x is 1. Remember from the above here, y is 2 when x is 1. So I'll put 2 for y, 1 for x. That's 4 minus 1, so that equals c. So c is 3, so I could rewrite it like this. Y squared minus x squared equals 3. And sometimes you leave the answer like this, but if you want to write it explicitly in terms of y, we can solve that for y. So this is what I did over here. I just added x to both sides. So move the x over there. So y squared equals x squared plus 3, and y equals the square root of x squared plus 3. Now, this could be plus or minus. Y is at plus. Well, note, since when y equals 2, x equals 1, well, if I thought of the negative square root, because it could, usually when we take the square root of both sides, it's plus or minus, but if I think of the negative square root, and I try to substitute my initial value in, so y is 2, and x is 1, okay, 1 squared is 1, 1 plus 3 is 4, but this would be negative 4, or the square root of, I'm sorry, negative the square root of 4, which is 2, but 2 does not equal negative 2. So y cannot equal the negative square root. If we try the positive square root, y equals the square root of x squared plus 3, and I put 1 and 3 in there, I do get 2 equals the square root of 4, so that's okay, so that works. So that's why it would be the positive square root. Okay? Hope you can all see that all. So that's why we have the positive square root. And sometimes you do have to check them like this using this initial condition to verify that. I've seen that on some of the AP exams. And the domain, there's no real issues here, so the domain would be just from negative infinity to infinity. All real numbers would suffice. Okay? That's number 1. Let's take a look at number 3. And again, here's another differential equation. Dy dx equals y over x. Y equals 2 when x equals 2. So again, we'll separate the variables. So we'll have 1 over y and then the 1 over x dx. So we put the dx over here with the 1 over x, and we put the 1 over y with the dy. Then we take the integral of both sides. So we have the natural log. So we have 1 over y dy, 1 over x dx. We take the antiderivative, or the integral, and we get the natural log of y equals the natural log of x plus c. So taking the antiderivative. And then, in order to solve this, I could write this as an exponential equation. What's my base? My base is e. What's my exponent? That's my exponent, natural log of x plus c, and what's my answer? Y. So that's what I have, so I can flip this, and I can put the y on this side, and I can write this. Then I can break this up as e to the natural log of x times e to the c. And I can put this, I can call this just e to the c as a constant. So we can call this c times e to the natural log of x. Okay? All right, what's e to the natural log of x? Well, there's a couple ways to look at this. You can use the definition. Remember, the natural log is an exponent. This is the exponent. Then when I raise e to it, I get x. If you use the definition, this is the exponent, that when I raise e to it, e's the base, I get x. Well, since I'm raising e to this exponent, I should get x. So I could say that that equals x. If you wanted to do it a little bit more analytic or mechanical way, you could just say, well, what is the e to the natural log of x? What is that? I can call that y. Then I could take the natural log of both sides. So the natural log of e to the natural log of x equals the natural log of y. Then I could use my property of logarithms and put this natural log of x in front. And the natural log of e is just 1, we know that. So then I would have the natural log of x equal to the natural log of y, and since the natural log is a one-to-one function, if the left side equals the right side, and they're both the same base, then this has to equal that. Sometimes they call that the argument. So x equals y. Well, if x equals y, and y is this, which is that means that x equals e to the log x. So in either case, we get this. And then we substitute our known values. In other words, y is 2 and x is 2, so I put a 2 for y, a 2 for x. And then I divide both sides by 2, so 2 over 2 equals c, so c equals 1, so it's just y equals x. Now we do have the natural log of x in this problem, and remember that the domain for that is always x has got to be greater than 0. So that puts restrictions on my domain, so my domain will be from 0 to infinity. Because that's the domain of the natural log of x. Okay? All right. So I hope that helps.